Good morning, everyone. I heartily welcome you all in this online refresher course in chemistry hosted by Department of Chemistry, School of Sciences, Gujarat University, Ahmedabad, on behalf of Dr. Jagdish Joshi, Professor, Director, UGC HRDC, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, Department of Chemistry, School of Sciences, Gujarat University.
Welcome all. I am Siddhi Panchal from Department of Chemistry, School of Sciences, Gujarat University. In the next session, we would encounter Dr. Rajesh Kamble, Professor, Department of Chemistry, University of Mumbai. He is having 20 years of experience in teaching and research. His thrust area of research interest include designing, synthesis, and characterization of novel AIE functional organic materials for application in OLEDs, solar cells as chemosensor and for bioimaging purpose. He has done supervision of 84 MSc projects, has guided 2 PhD students, and currently have 6 PhD candidates under his guidance. He has fruitfully completed 3 research projects funded by UGC, DST SERB India. He has total 33 publications with 6 national and 27 international. Moreover, he is reviewer for journals like RSC Advances, Chemistry Select, New Journal of Chemistry, Journal of Material Chemistry, Journal of Molecular Structure, Journal of Chemical Sciences, and many more. He has also presented 40 papers and conferences at national and international level. He has delivered 11 lectures at various universities, research institutes in conferences. Additionally, he was secretary of UGC SEP-sponsored National Conference on Research Development in Chemical Sciences 2018. He has also served as coordinator of refresher courses and worked as coordinator of IQAC in various committees at university level.
Dear participants, this is Dr. Rajesh Kamble from Department of Chemistry, University of Mumbai. It's my pleasure to deliver this lecture, this online refresher course in chemistry organized by Gujarat University and its UGC HRDC Center. The title of my lecture is Novel Functional Organic Materials for Applications in Organic Electronics. The outline of this talk is I'll discuss some about the discovery of organic molecules which can act as in semiconductors, applications of these organic semiconductors, the current scope and development of organic semiconductors, its classifications, the term aggregation-induced emission, which is purchased by some molecules that warrants the application of these kind of materials, solid state application of these materials in optoelectronic devices, and our efforts to meet the present requirement in the field of organic semiconductors. So let me talk about the history of these organic semiconductors. In past, it was thought that organic compounds are insulators, but Martin Pope and his colleague Kalman, they showed that these organic insulators convert into semiconducting materials when the charge carriers are injected using the electrodes. These organic semiconductors are nothing but the organic compounds which possess similar properties like inorganic semiconductors with holes, electron conduction layer, and a proper band gap. Organic semiconductors are the compounds whose building blocks are pi conjugated molecules. Small molecules, these are called as oligomers, or the polymers of large molecules, which are made up of carbon and hydrogen, and sometimes possess the heteroatoms like nitrogen, sulfur, and oxygen. In 1973, the trio Alan J. Heger, McDiarmid, and Hideki Shirakawa, they reported the high conductivity in oxidized and iodine-doped polyacetylene, a polymer molecule. And for that invention, these three were awarded Nobel Prize in Chemistry in 2000 and for the new class of these materials, that is conducting polymers. In 1987, Tang and Vance Lyke from Kodak Laboratory, they fabricated the first organic electroluminescent device, that is OLED device. And later on, Sony introduced world's first OLED television in 2007. In 2014, the Nobel Prize in Physics was awarded to this technology. And the technology is for the development of efficient blue light emitting bulb. And again here, these are the trio, Professor Akasaki, Amano, is a student of Akasaki, PhD student, and Nakamura for development of efficient blue LED. Because green, red, yellow emitting materials are well known. Majority of materials, they emit these lights, but blue light emitting and white light emitting materials are very rare. And these researchers, they recognize that gallium nitride would lead to a blue color and discovered a way to produce the light in an efficient way by adding the aluminum and indium as an dopant. So they started this research in 1988 and got Nobel Prize in 2014. So this is the third time the Nobel Prize was given to pure technology, because for technology actually the Nobel Prize is not given. So this is the third time. And what the Academy wrote here, writes, incandescent light bulb lead the 20th century, but the 21st century will be led by the light emitting diode lamps or LED lamps. So that is organic semiconductors, they have application in display technology as well as lighting technology. You can see the blue LED here. Okay. Now, if you see the applications of these organic semiconductors, they are used in what? Organic field effect transistors, organic light emitting diodes. Nowadays, we have the flexible OLED displays, organic photovoltaics used as a solar cell, RFIDs, and organic lasers. And within this kind of the organic semiconductors or these molecules, the DA molecules, D stands for donor here, A stands for acceptor. Means within a molecule, the one part it acts as an acceptor and other it acts as a donor. And the electronic transitions takes place within this molecule from donor to acceptor when these molecules are excited. Now, these DA molecules have been extensively synthesized and investigated in the last few decades for their potential application in the field of all these OFETs, OLEDs, PDs, RFIDs, and organic lasers because of their unique charge transfer properties. Now, if you see the development in the field of optoelectronics, that is the display technology. So, in past, we were using the big televisions. The televisions sizes were very big because in that use the cathode ray tubes. Now, this is what a first CRT television came into the market in 1934 by this company Telefunken in Germany. Then in 1988, first commercial LCD, that is liquid crystal display television, was introduced by Sharp Corporation in Japan. And then in early 90s, the first LED, that is light emitting diode television, came into the market. And now this is the area, today is the area of organic light emitting diodes and AMOLEDs, that is active matrix organic light emitting diodes. And the first organic light emitting diode television was introduced in 2012 by Samsung company. And you can see, I can see the screen of cameras, okay, made up of OLED technology, and the screens of mobile phones or the tabs are having this AMOLED display. About the lighting technology, these organic semiconductors, they are used to make to light our houses, malls, the signals, the boards at the airport, many places. So this is the incandescent bulb or the tungsten filament bulb, and now replaced by this compact fluorescent lamp, that is CFL lamp. And nowadays we have this LED lighting. So this is what again has its many uses, like say from the toys of the children's, like yo-yo something. Okay, so we use the small these LEDs. We used to lit our houses with these LED lamps. Okay, even though the cars indicators made up of are having these LED lamps. So this is what the development in the technology of the lighting. Now we'll see the comparison between organic semiconductors and inorganic semiconductors. So why these are superior? Now in case of the processing, how the making of again the displays. In case of organic semiconductor, no vacuum or no high temperature processes are required. But in case of inorganic semiconductors, ultra clean room are required and the process is highly costly. Cost of organic semiconductor processing is a low cost, high production, that is $5 per square feet. In case of inorganic semiconductors, the cost is very high, that is $100 per square feet. Advantage in case of organic semiconductors, these are lightweight, flexible, compatible with plastic and paper substrate, and high electron mobility, and these are biodegradable, eco-friendly. And inorganic semiconductors, they are rigid and should be prepared on a glass substrate or any of the rigid substrate, have the low electron mobility and non-biodegradable. But if you see in case of efficiency, the organic semiconductor, they have the disadvantage as compared to inorganic semiconductor. The lifespan of organic semiconductor is still low as compared to the inorganic semiconductor, but the improvement is going up. But inorganic semiconductor devices, the lifespan is much more as compared to the organic semiconductors. Again, we see the advantage of OLEDs over LEDs. OLEDs is what organic light emitting diode, or light emitting diode where we use inorganic material. Now, in case of the thickness, OLEDs, organic light emitting diode televisions are thinner than LEDs, often less than 1 inch, or nowadays we have just half centimeter thickness of these OLED screens. But inorganic LEDs, they have the thickness is more than OLED televisions and requires the backlight. The backlight illumination is required, but thinner than the CCFL LCD televisions. Power consumption is required less in case of OLEDs, around 70% compared to LED, and LED requires less power than the LCDs and the plasma television, that is your CRT televisions. Lifespan, the recent improvements which showed the lifespan of these OLED televisions is up to 43,800 or up to 50,000 hours and in case of LED, it is around 1 lakh hours. The viewing angle is very high in case of OLEDs, that is goes up to 170 or 180 degrees centigrade. You can see this is the curved television, OLED television. You can see this picture of tree at any angle, so that does not get distorted. But angle of viewing in case of LED is very less. Backlight in case of OLED is not required. In case of LEDs, the back illumination is what required. Contrast ratio in case of OLED is very high. In case of LEDs, very poor. And about the weight, OLEDs, they are very lightweight as compared to LED. And LEDs, they are lighter as compared to the plasma television. You can see the curved televisions which are connected in series, and we get the big screen. Okay, so this is the benefit of what the organic light emitting diode. Now come to the classification of these organic semiconductors. Organic semiconductors, these are classified on the basis of their molecular weight and their electronic properties. On the basis of molecular weight, these are again categorized into small molecules and the polymers, that is large molecules. And on the basis of electronic properties, they are categorized as p-type or pole transporting material, n-type or electron transporter, and ambipolar, that means which can transport both the charges, that is hole as well as electrons. Now the remarkable properties of organic materials. These organic semiconductors are easily prepared, easily synthesized. The synthetic routes are easy as compared to this inorganic material or semiconductors. We can modify easily the structure of these organic materials and tune the photophysical and electrochemical properties. These have the great solution processability with better solubility in many organic solvents, but inorganic materials, they are very poor solubility in many organic solvents. And we can easily shape and manufacture the devices using organic semiconductors. So you can see here the organic jet printing on this flexible substrate, and this is what a flexible OLED screen. So it's very flexible. Okay, now let's go. Now, importance of DA architecture. So in previous slides, I just talked about this DA, donor-acceptor kind of this architecture of molecules. So in which the one segment is having the acceptor property, electron acceptor property, and other is having electron donating property. This forms this DA architecture within a molecule, which facilitates the ICT, that is intramolecular charge transfer. Like we have this inorganic charge transfer complexes also. Metal organic, organometallic complexes. They show the charge transfer spectra. So like here also, when we take the absorption spectra, when we characterize these molecules, okay, photophysical data or absorption spectra, so there we can see the ICT, that is intramolecular charge transition. Decreases the band gap. The band gap is what silicon is most widely used in organic semiconductor, which has the band gap 1.3 electron volt. So we can reduce the band gap of these organic semiconductors of these molecules up to what 1.3, 1.4, or 1.5 here towards silicon, which gives the facility to structure modification, extend conjugation. We can add the more aromatic systems or conjugation in these DA molecules, which are responsible for active charge transfer, either hole or electron or both the charges. This DA architecture allows to tune photophysical, electrochemical, thermal properties and helps to induce AIE property in the molecules to obtain the solid state emissive material. So AIE here stands for the aggregation-induced emission. So I'll come to that point in the next slide. Also, this DA architecture in the molecules induce thermal stability in the molecule, because these kind of molecules used in the fabrication of devices or the OLED devices or in lighting technology, they should withstand up to what 80 degrees centigrade temperature. So these molecules, they have this higher temperature, higher stability, okay, above 150 degrees centigrade and like that. So we'll see the in detail about this P-type, N-type, or ambipolar kind of these materials. So P-type materials are also called as the hole transporters. These are the materials which have low ionization potentials, low IP values, and low electron affinities. That means these are having electron donating properties. And these are some examples which are commonly used or reported in literature as the electron, the P type of material, or the hole transporters, TPD and NPD. N-type materials are also called as electron transporter, having high ionization potentials and high electron affinity. Means they have the electron accepting properties. And the examples are perfluoropentasine and this naphthalene diamides. The third kind of these materials are ambipolar materials, which can have the both properties, that is as an hole transporter as well as electron transporter. These materials can provide both N and P channel performance. And the examples are Tyrian purple and Tipstone. Now, various DA molecules having triaryl amines fragment as a donor unit show the good hole transporting properties. I'll tell you about this what triphenylamine, so which is very good P type of material of the hole transporter and emitter also used in optoelectronic devices. The outstanding development in hole transporting materials witnessed higher mobility than the amorphous silicon, that is approximately 1 centimeter square per mole per second. But the development in the electron transporting material, that is N-type and ambipolar material, is still lagging far behind as compared to the hole transport materials. So till date, the hole transporting materials are developed in large, but N-type and ambipolar are few. So what is the reason? The reason is what? To develop this N-type and ambipolar materials, the difficult synthesis and unstable under ambient conditions like the oxygen and moisture, that is water, so which interfere with these devices or lowers the performance of these devices. So that's why the importance of this N-type and ambipolar kind of materials, that is the electron transport materials, are the indispensable components of integrated circuits. And ambipolar semiconductors can provide both N-type, N-channel, as well as the P-channel, that is the hole, in a single device. So there is no requirement of separately using the P-type and the N-type semiconductors. Now this is the triphenylamine molecule, a simple organic molecule, which is a non-basic, contrast to most of the amines. So this is the molecular formula at 3 phenyl rings. This is the tertiary nitrogen. And the derivatives, this triphenylamine and its derivatives, they have useful properties in electrical conductivity and electroluminescence and are used in OLEDs as a hole transporters. Because these triphenylamines, they have ionization potential value 5.3 electron, which make it suitable for injection of holes from the ITU into the attached molecule. ITU is we use as an anode, okay, in the fabrication of device. Ionization potential, ITO, its IP value is what, 4.8 electron. It is used as an anode, the indium tin oxide. Ionization potentials of triphenylamines may be varied. Now, if you substitute this for triphenylamine, to get the derivatives and the ionization potential values, we can vary or change, get within 4.9 to 5.9 electron by substitution. Now, this slide here, you can see the device structure, a single layer device or this multi-layer OLED device. Now, the single layer device here, we take the glass substrate on which we used to coat or transparent anode, that is indium tin oxide is widely used as an anode. A thin layer, layering what is nanometer again. Then on which we used to coat the emissive layer, that is organic molecule, and on that we used to coat a cathode layer. And when we apply the potential, okay, the holes are injected into the HOMO of emissive layer, and the electrons are injected by the cathode into the LUMO of this emissive layer, that is organic layer. And both these holes and electron, they transfer within this emissive layer, met somewhere, form the exciton, and then this is the exciton, and this decays with emission of a characteristic light as a blue, green, red, yellow. Okay. So this, you can see the Samsung OLED, organic light emitting device, a screen, where you can see these are the pixels, number of pixels here you can see of blue, green, and red. Okay. And there is a great demand of ambipolar and solid state emissive materials in the development of organic electronics. This is the design of a multi-layer OLED device, which is having a complex structure. So where is to take the glass substrate and coat the anode, then is to apply the whole injection layer, whole transport layer, electron blocking layer. Then this is the emissive layer, organic layer. Again, whole blocking layer, electron transport layer, electron injection layer, and this is the cathode. So, but the efficiency of this multi-layer OLED is much better than this what the single layer OLED device. Now, this is what the effective masses of electrons hold. Just I told you the mechanism here. The electrons jumped from the valence band to the conduction band, and the free electron thus creating the holes and electrons and forms the excitons, and then decays to produce that characteristic light. These are the pictures here. You can see the demonstration of flexible OLED device. Okay, it's a flexible substrate we to take on which this water device is fabricated. So when we apply the potential, okay, by using the 3 to 5 volt or up to 6 volt here, okay, with the help of crocodile pin, the batteries we used to apply the potential, and we see this green light here. This is also the green yellow light here, the green emitting OLED device. Okay. These are the devices. Then come to the that another that phenomena that is it's not much very known, that is aggregation-induced emission. Now, organic materials or the molecules with efficient solid state emission, these are highly required for various optoelectronic applications, particularly for organic light emitting diodes. Because ultimately many organic molecules they show good emission in their solution state, but when we form a thin film of these molecules on a substrate, so the emission quenches or emission decreases. And the phenomenon responsible for that quenching of emission is the aggregation caused quenching. And this term AIE and ACQ was first time coined by Benzone in 2000. Now this aggregation caused quenching, this effect is attributed to the non-radiative deactivation processes such as excitonic coupling, hexamer formation, and intramolecular excitation energy transfer. That's why for organic light emitting diodes, the organic compounds of the fluorophores, the emissive molecules are generally used as a dopant, that is the guest emitter, which are dispersed in a particular appropriate host matrix. Whereas the application of non-doped material is what restricted. But to simplify the device structure and fabrication process, it is desired to construct highly efficient OLED with non-doped emission layers. Now in 2001, Ben Zhongtang and his colleagues, they discovered an interesting photophysical phenomena that is termed by them as an aggregation-induced emission. When the molecules get aggregated, comes close to each other, becomes emissive. But the same molecules in their solution state are non-emissive. It's a very quite interesting term to come for this AI term named by this term AI, aggregation-induced emission, which has been proved to be an effective approach to suppress the concentration, quenching, and to attain the efficient solid-state process. Now, in AI process, the non-emissive molecules are induced to emit by aggregate formation, derived from the synergistic effect of the restricted intramolecular rotation. Restricted intramolecular rotation. The next slide you will come to know what is this RIR. So what the molecules they prepared, they synthesized and found this RIR process or mechanism by which the emission enhances and the highly twisted molecular conformations, which reduces the intermolecular pi stacking. They are also observed in cellular derivatives. The aggregation worked properly. Cellular derivatives are non-emissive in solution state, but highly luminescent in concentrated state or into the neat solid films. And this phenomena of enhanced emission or aggregation of these molecules is AI. So that's why a series of AI fluorophores prepared by Tang and his colleagues, including cellulose, cyanosteel beans, tetraphenylethene, and orthocarbon derivatives, reported by them, and their work is highly cited. And these molecules are non-luminescent in direct solution, but become highly emissive upon formation of aggregates. And on the basis, some of AI active fluorophores have been developed as emitters for efficient non-OLEDs. Now, here you can see the structure of these molecules. That is the hexaphenylsilol, reported by this Tang and his colleague in Chemical Communication in 2001, first time, 19 years back. And they gave it many papers in the highly uh, uh, high impact factor journals. So this is the hexaphenylsilol. Centrally is the silol here, and 6 rings are the phenyl here. RR is also phenyl ring. And this is what tetraphenyl ethene for the ethene. I will see the 4 phenyl rings. So what makes these molecules as AI active? So you'll see. The principle behind AI activity is that you can see they have the perylene is a condensed molecule, aromatic system, emissive in its solution state, but becomes non-emissive or emission quenches when it gets aggregated on its solid state because of pi stacking. So this forms again the pi pi stacking interactions takes place, okay, of these aromatic rings. It's like a formation of the pi. HPS, that is the hexaphenylsilol. So the central silol, it acts as a stator which can't move, and the 6 phenyl rings, these are rotatable. Now this hexaphenylsilol is non-emissive in its solution state, but in aggregation state, the emission enhances, it becomes emissive, highly emissive, because of restriction of intramolecular rotation. Now the factors responsible for ACQ, that is aggregation cause quenching in A, this perylene, are the planar geometry, which tend to aggregate as a disk pileup. The molecules are piled up on each other due to strong pi stacking, and that's why the emission turns off. While the non-planar luminogen molecules like this hexaphenylsilol, the B, behave oppositely. Their emission in solution, okay, turn on in the aggregate state due to restriction of intramolecular rotation because of the multiple phenyl rotors. So you can see here the interaction between the molecules, intermolecular interaction is somehow different as compared to what is the perylene in solid state. Again, you can see the very famous dye, that is the fluorescent green emitter. So it is highly fluorescent in solution state, but in aggregate state, it is non-emissive. In case of tetraphenylethylene, this is purely non-emissive in solution state, but in solid state, it is highly emissive. So because of this RIR, that is restricted intramolecular rotation phenomena, so that gives the non-planarity, okay, to these molecules, and the geometry is a non-planar. So that's why it shows the emission, good emission in solid state. Therefore, the propeller-shaped non-planar geometry of immersion helps to govern or reduce the ACQ problem and to convert that non-emissive molecule into emissive one. Triarylamine is AI inactive. Now, triarylamine, see, I showed you in the previous slide, the triphenylamine, it is AI inactive. It is emissive in solution state, but solid state is AI inactive. But when attached to an electron deficient aromatic moiety, result into AI active species. Now, quinoxaline, these are the molecule having the imine groups within it, that is nitrogen atoms. They have the outstanding electron accepting properties because of the strong electronegativity of its two nitrogen atoms present in the imine form, and its stable quinoid structure, which gives remarkable photophysical properties like unique absorption and emission and high charge carrier mobility. So thus, by considering, keeping in mind the importance of donor-acceptor kind of architecture to obtain the ambipolar kind of materials or organic semiconductors and AI properties within, what we have done or we contributed to this field is what? We have selected the quinoxaline core as an strong electron acceptor, and the donors are the electron-rich triarylamines or the heterocyclic amine as a donor. Now, these are the donor-acceptor based AI active molecules reported with triphenylamine and N-phenylcarbazole donor units. Now, you can see these are the molecules here. Okay, triphenylamine derivatives. Okay, having this carbazole, they are heterocyclic. These are the phenyl rings. Here, again, see this chlorinol and anthracene derivatives. So these are reported in this one as an AI active molecules. Now, our efforts or our contributions, so which is what again adds some importance of these kind of molecules for this AI phenomena and in the field of organic semiconductors. Now, this is the first scheme I'll show you here. So, what we have done in our research lab, in our research group. So, we have taken this quinoxaline. So, this quinoxaline is having this nitrogen atom as an electron deficient moiety as an acts as an acceptor, and to this we have added the donors. Now, R1 and this R2, these are the donors we have attached to this electron deficient quinoxaline. So we have diphenylamine, naphthylphenylamine, having methoxys electron donating groups on diphenylamine, having electron withdrawing nitro substituent on diphenylamine, and a heterocyclic donor like a carbazole. And we studied in detail the photophysical, electrochemical, thermal, and theoretical studies also of this molecule to get ambipolarity nature in these molecules and the AI properties. Now, to show first of all the ICT architecture in this molecule. Now, these are the DAD kind of models. Okay, we have prepared. DAD is what here? So this can act as a central moiety as an acceptor quinoxaline, and we added donor on these three sides. So this becomes donor, acceptor, and donor. So these are the donors: diphenylamine, naphthylphenyl, having methoxy, diphenylamine, and this is the carbons. So we have taken the photophysical data of these molecules in various solvents. In table, this you can see the data in toluene and the solid film also. Now in toluene, you can see here the absorption data. This one first compound is what this is the central moiety, the quinoxaline, and second, third, fourth, and fifth are this donor amine. Now you can see here, in case of one, the central molecule only, it shows only the N to pi star and pi to pi star transition. But when you attach the donors to this electron accepting phenoxylane, a new band above 400, absorption band above 400 nanometers was observed, and this is assigned to the intramolecular charge transfer, ICT, transition from electron donor group to electron acceptor. Thus confirms the formation of DA architecture, donor acceptor architecture, that is highly required in case of these organic semiconductors or these electron-missing molecules. In case of solid film, again, see in case of this central molecule, the reactor is to say where is to add this donor. So you can't see here the ICT band, but in other 2, 3, 4, 5 these derivatives, you can see this ICT transitions. We have taken the emission properties of these molecules in solution as well as the solid film. In toluene, this is the data here. The central molecule is an electron acceptor, electron deficient is a non-emissive one, and when we attach the donors and form the DA architecture, the mole molecule becomes an emissive one, and this emits in what, green to yellow to blue region. So carbazole, having seen the carbazole donor, it emits a blue light, having this methoxy electron donating substituent on diaphenyl, emits in what, 534 parallel, and having diaphenyl amine or naphthyl amine again emits in what, cyan blue color here. In case of solid film, you can see the bathochromic shift in the wavelength because of the aggregation of molecules in the solid state, and you can see the peaks at a higher wavelength, that is the bathochromic shift. And the Stokes shifts are also very good, and you can see the quantum fluorescence yield of these molecules are again this very acceptable as compared to what the standard emitters will use. Now this is what an absorption plot of these 1 to 5 molecules. One is your central core moiety, the phenoxylane moiety, and when you attach these amines, you can see here N to pi star, pi to pi star transitions due to for the whole molecule, and ICT above 400 nanometer is due to the charge transfer from donor amines to what, the central phenoxylane. Now these pictures you can see these molecules in their solution state, and this is what the solid state. Okay, so the solid absorption spectra of these compounds also you can see here. So the ICT, the characteristic that is this peak, which confirm the DA architecture. And these are the right side emission spectra of 1 to 5 in toluene and in solid film, late solid film. Now you can see all the molecules, they are emissive in the solution state, particularly the second molecule and this third molecule, that is the diphenylamine and naphthylamine. One is non-emissive, this having this good emission, but in solid state, the molecule having carbazole donor, it shows a very good emission, okay, up to 550, that is the emission intensity as compared to the other derivatives. So here also you can see the solid state, the second, third, fourth and fifth derivative. The fifth having this carbazole in it is a blue emitter, and these are the green emitter, this is the yellow emitter. So this again suggests that the molecule, the sixth molecule, okay, this molecule which is having, the fifth molecule is having this carbazole donor, the heterocyclic donor, has this good emission in the solid, in its solid state, and thus can be have this E property. So we'll see the structures of these two molecules. The second is what the having diphenylamine, okay, at 3 places here, and central core is the acceptor, donor acceptor, and this is what the rigid carbazole, okay, 3 donors to this what the central acceptor. Now in case of the second molecule, and these are the optimized structures of this molecule 2 and the 5. You can see here the structural difference. Now this molecule second is having this diphenylamine donor group, so which has the 2 freely rotatable phenyl rings. Okay, they can rotate and give some planarity to this molecule or some geometry to this molecule, the two rotatable phenyl rings, more degree of rotational freedom is there between the C and N bond, and lesser intramolecular steric hindrance is there. And that's why these are good emitter in their solution state, but in the solid state, so these are weakly pi active. But when we have this carbazole as an electron donor, we can see there the locking conformation of phenyl rings. Here, in this, we have a new bond between this carbon and this carbon of these two phenyl rings, so it becomes a carbazole. So these free rotatable phenyl rings, now the rotation get restricted because of this locking, okay, conformation of this phenyl rings. Now this molecule becomes the residual. So that's why there is a lesser degree of rotational freedom, and there is a large intramolecular steric hindrance, and thus this molecules is strongly pi. In its solid state, it emits strongly, like you can see here in its solid film. This molecule is having carbazole, that is the donor group, emits strongly, but in solution state it's having the weak emission. And here you can see the effect of difference in degree of rotational freedom on ICT maxima in 2 and 5. Now this is the absorbance spectra taken in solvent toluene. So you can see the ICT in second molecule and ICT for ICT in 5 is water weak, but it is strong in case of 2 molecule having diphenylamine. But in solid film, the ICT, the characteristic transition in case of this fifth molecule having carbazole in it, the resid donor unit is much better as compared to the second molecule having the two rotatable phenyl rings. Now, effect on photoemission spectra of 2 and 5. If you see the emission of these 2 and 5 molecules, again in solution state, that is the toluene, and the solid state, you come to know here this molecule 2 having diphenylamine is a strong emitter in solution state. It emits at 494 wavelength, is a green emitter, and fifth molecule having carbazole unit, the emission is what less, the weak emitter at wavelength 459, that is the blue emitter. But when you prepare its solid film, the molecules come close to each other, gets aggregated, and in that aggregated state, fifth molecule having carbazole donor, a rigid carbazole heterocyclic moiety, becomes strong emitter, and you can see very nice emission at 487 nanometer. And the second molecule having the diphenylamine unit, it emits at 530, that is in the green region. You can see here the solid film emission pictures of these 2 and fifth molecule. Okay, so thus the having seen a different donor moieties from the central core, that is the acceptor, the absorption as well as the emission properties of the molecule it changes, and also that affects on getting the good AI properties within the molecule. Now, principle behind AI phenomena causes in die 2 and 5, we should have to get the strong solid state emission. It's due to the reduction of rotational degree of freedom. Like in case of the second molecule, there we can see the two phenyl rings which are rotatable, okay, and in case of molecule fifth, that is where we have this carbazole as a donor, the heterocyclic amine, okay, the resid moiety. So there we can see the restricted intramolecular rotation interaction in the aggregate cell. That's why the fifth molecule is having the good emission in solid state as compared to the second. It suppresses the intramolecular steric hindrance, increases the intramolecular interaction in the molecule. The molecule should interact properly, like see, we have seen the mechanisms in case of the beryllium. The pipette stacking takes place, so that's why the emission quenches in the solid state. But in case of the hexaphenylsilol, so because of this propeller shape or the non-planar nature, okay, and restricted intermolecular rotation, the intermolecular interaction takes place, like see the head to tail, something like that, or J kind of see the interaction or the aggregation. Now here the twisted conformation or the non-planar conformation tend to become the coplanar in the aggregate state of these molecules, and thus shows the aggregation-induced emission effect. Now again, see this AI phenomena of this molecule fifth having carbonyl donor unit was studied using the mixture of two solvents. Now the AI properties of phi investigated by fluorescence spectroscopy using different pH of water fractions, and this luminophore is highly luminescent in high water percentage, which confirms the formation of nano-aggregates and having the AI properties. For this, we have taken the vials in which this molecule is what again dissolved in THF. Now, this first vial you can see here the 0% of water. Uh, this molecule is what is good, showed the good emission in what THF, organic solvent. Then we add successively the 10% successive addition in each vial the water. This more polar, that is this solvent, highly polar solvent, the 10% here, 90% of THF, 10% water, then 20% water, 30, 40, 50, simultaneously reduce the percent of THF. Now, if you can see, when you add see the percentage of water, a water fraction, 10, 20, 30, 40, 50, you can see here the emission quenches. And at a particular say the THF water system here, that is 60% water fraction, you can see again the emission regains. And that is formation of, due to formation of the solid nanoparticles of the luminescent phi. You can see here, these are the pictures of the vials in the visible lab. You can see here the homogeneous suspension of nano-aggregate formation, and you can see here in the UV lab, okay, the emission of this, okay, THF water fraction, this molecule in the THF water fraction at 70%. Now you can see here the plots. The in THF, this luminescent phi, it shows the wavelength 482 nanometer, and this you can see the increase in wavelength. So due to the positive solitochromic effect here, the water fraction is what increases, the polarity of the mixture of this solid is what increases. That is called as the positive solitochromic emission quenches. And the wavelength, you can see the bathochromic, that is the shift in the wavelength is observed, and that is the phenomena, that is the positive solitochromism. But a stage comes where the polarity of this water, increasing fraction of the water, and the polarity, it becomes null, and formation due to formation of this aggregates of this molecule, and there see the positive, the solitochromic effect is what the negative, and due to formation of the solid particles or the nanoparticles of this dye, so you can see the emission over here. So at this 60% water fraction, you can see this wavelength is 487. This is here about the same. Now you can see the 60% fraction of water, THF water. The wavelength is 487, and the emission wavelength of this solid thin film of molecule fifth is again the same. Again, you can see the quantum yield of this molecule in its different water fraction. In pure THF, it shows 0.66, and quantum yield, it goes down. Okay, when you increase the water fraction, it is becomes 0 at 50%, but suddenly rises at 60%. That gives us the 0.40 as compared to what the reference we have taken here, fluorescein. So which is having this quantum yield 0.1 molar NaOH. So thus this indicates, I can see this formation of nanoparticles is confirmed by the plotting the absorption spectra of all these fractions. Okay, all these fractions tend to what 90% water fraction in THF, and you can see at 60% here of water fraction, the leveling of tell you can observe, and that phenomenon is called as the mice scattering. Scattering of light at this percent of water fraction indicates the presence of nano-aggregates. So this is called as the mice scattering. That again, see, this confirms the formation of nanoparticles, and this is the emission spectra taken for all that percentage of water fraction from 0%, that is the THF, pure THF, to water to 90% water. Okay, you can see here The wavelength in pure THF is 482, but at 60% here, you can see the wavelength is 487. So that you can see here in this spectra. That formation of nanoparticles can be further confirmed by taking the SEM spectra, scanning electron microscopy spectra of these nano-aggregates, which are formed in 60% of water fraction. So this is the bar diagram. Again, you can see the emission intensity versus water fraction, volume water fraction. So at THF, it shows this emission intensity. But when you increase the water fraction, the emission quenches. And at 60%, okay, this is what a 0% water fraction, that is THF. It shows the emission. Up 50% is emission quenches, and at 60%, the fraction of water, due to formation of these nanoparticles or the aggregations or solid particles of this word, the molecule fifth having carbon or donor in it, the emission, it rises and shows the aggregation-induced emission phenomena. Okay, but the emission you can see here, the decreases due to the different conformational changes in these molecules, and the particle size of nanoaggregates are found between 19 to 40 nanometer. So this is what about this photophysical study, the absorption emission properties of this molecule, and how this change in donor moieties affects on this absorption emission phenomena, as well as to acquire the AIE properties in the molecules. Now, by characterizing these molecules electrochemically, that we use the cyclic voltammetry technique, and by which we studied the redox properties of this molecule, where you can see here this molecule one is what your central moiety, the acceptor phenoxanine. So it shows only the reduction peak because it's an strong electron acceptor, and there is no oxidation peak, but when it adds these electron donors here, so we can see the three oxidation peaks, and these are attributed to the oxidation of these amine groups. And the single, that is the reduction peak, is what constant in all these derivatives. And using this oxidation and first oxidation and reduction, these values, by using this formula, we calculated the HOMO and LUMO, and getting the HOMO LUMO values on the basis of these HOMO LUMO values and comparing these HOMO LUMO values with reported ambipolar or widely used ambipolar materials. We used to conclude these molecules as ambipolar materials with good electrochemical band gap. So if you see in case of this acceptor, it's having band gap 2.9, and when we have this DA kind of the architecture or adds the donor to this acceptor moiety, the band gap get reduced to what 1.87 in case of second molecule, 1.88 in case of third, in fourth is 1.68, and in fifth is 2.19. And you can see here the HOMO level in case of your core moiety, that is the phenoxanine acceptor, it is goes above 6.50. That is much lower. Actually, to have this P type of series character, that is the whole transporting character in the molecule, the ionization potential or HOMO level, it should be between 4.8 to 5.8, and to have this N type of property in the molecule, that is electron transporting, the LUMO value should be within 3 to 4 electron volt. Now you can see here the HOMO of these molecules are 5.51, 5.52, 5.35, 5.72, and LUMO is 3.64. Now this is what again see the LUMO here. We used to tune the HOMO properties, HOMO values of these derivatives, and keeping constant the LUMO, that is the N-type characters of these derivatives, which is there in case of this reactor, that is the central one. So the DA kind of architecture, again, this is the cyclic voltammetry you can see here. Okay, theoretically calculated, again see the data, and just observing this molecular orbital diagram of this molecule, second molecule, you can see here the HOMO, the electron density, it lies on whole molecule, but in LUMO, that means when the electronic transitions takes place from donor to acceptor, the electron density you can see totally on this central acceptor model. So thus this indicates or confirms the formation of DA architecture within this molecule. Now this HOMO and LUMO level of these molecules, that is the second, third, fourth and fifth, is compared with the standard. So standard is what again is cyclopentane acetylene derivative. So it's a ambipolar material, is commonly used, reported in literature. So which has the HOMO value 5.35. Is what again these values, HOMO values of derivatives of this quinoxalone, what again you can see similar to this what HOMO of the standard, and LUMO of this standard is 3.67 and LUMO of these derivatives are close to what the standard one. So on the basis of this compared HOMO and LUMO values comparable with the reported not only the standard molecular ambipolar material but other ambipolar materials also. So we confirm that these molecules can act as an ambipolar materials. And this is what we reported in last year in New Journal of Chemistry papers. You can get more insight, more data in this paper. Now similarly, in second scheme, using the same central electron acceptor, quinoxalone. So we have see this both side. The R1 groups are see these electron donors like the diphenylamine, naphthylphenylamine, having methoxy and nitrosubstitution on diphenylamine, this carbazole. And R2 is what is a different group here. This is the benzoyl group here. So which again adds an electron withdrawing group. So which again make more deficient this quinoxalone thing. And we studied see the effect of this group on this electron acceptor, that is this side of this quinoxalone, and by adding these donors on this right side of this molecule. Now again we have studied the absorption emission properties of this molecule. This figure you can see here the images in solution state, again in visible and UV light. This is what a table against the absorption data given in what solvent, a non-polar solvent, toluene, and the solid film. So again, you can see in case of the first is in case of these derivatives, you can see the ICT transition. So that confirms the formation of this DA kind of architecture. Emission, you can see here these are the green and blue emitter. Again in solid thin film, so we studied the absorption and emission property. So where you can see this data. These are the plots here, absorption. So where you can see the ICT transition, and this is what the emission in toluene. Now all these compounds, they show the more or less intense emission in the neat solid film, and also the bathychromic shift of around 8 to 40 nanometer was observed as compared to toluene in neat solid film. So because of the aggregation, due to intermolecular aggregation of these molecules in that solid state. Now 2, 3, 5 and 6, these molecules, they show the good emission in their neat solid film, which again reveals the existence of aggregation-induced emission effect in this molecule. You can see here this emission plot in solid film or thin film. The molecule 6 having this carbazole unit shows the good emission of toward 800 emission intensity as compared to having this diphenylamine. Because of that, again, the RIR effect in the solid state. Now this AI property, I'll just focus on this AI property of this molecule. The AI properties of the 6 molecule that having which is having 6 carbazole unit on this on both sides, okay, investigated by fluorescence spectroscopy using different THF water fractions. And this luminophore is highly luminescent in high water percentage, which confirms the formation of nano-aggregates or nanoparticles and having these AI properties. Again, we studied these molecules in their different water fractions here. So you can see the 10 vials here, the molecules were emitting THF, pure THF, but when you add this water fraction here, the emission quenches show the positive solutrophobic effect. But at this a particular water fraction here, the molecule emits the light here due to formation of these nanoparticles or the nano aggregates, and thus confirms the AI property here. You can see here the emission plot here of all these fractions of cities. The mixture of THF water solvent, 0% of the THF is highly emissive, up to 650. But at 80% here water fraction, it shows the good, there is the emission due to formation of these nanoparticles or nano-aggregates or the solid state due to, again, see that phenomena, that is RIR. In the aggregate form, originated RIR, that is restricted intramolecular rotation due to physical constant blocks of the carbazole and that molecule. The non-radiative pathway becomes activate the radiative channel, which enables the molecule to emit strongly, and the presence of AI property indicates that the derivatives are good solid-state emissive materials. Now, if you see the electrochemical properties of this molecule, again, see the first molecule is what the common, as we studied in Titanium what's first key, is an N-type pure. But when you add these amines, okay, so you can get the oxidation peaks and calculated HOMO values. This one, LUMOs are within 3 to 4, HOMOs are between 4.8 to 5.7, 5.8. Band gap is what again is comes up to 1.58 electron volt and having a good thermal decomposition temperatures. And this is the CV plot here. And on the basis of this, what the HOMO and LUMO level calculated by experimental by cyclic voltammetry here. So this HOMO LUMO of these derivatives are compared with this standard molecule, that is the TRIPS pentacene, okay, which have HOMO 5.49 electron volt and LUMO 3.68 electron volt. And the Tyrian purple, another standard, HOMO is 5.5 electron volt and LUMO is 3.8 electron volt. And thus, comparable HOMO LUMO of these derivatives with these standards warrants the nature of these compounds or materials as an ambipolar materials. And this work is what published in Dyes and Pigments. So you get more information about the, in detail, see the discussion and the properties of these molecules in this paper. So in conclusion, so I can conclude that is organic semiconductors are the materials for this future generation, that is used for this lighting and display technologies. Whatever the derivatives I showed you in the scheme 1 and 2, these are the quinoxalane derivatives which are prepared by using quark emission reaction using palladium catalyst. We studied the photophysical, electrochemical, and thermal properties in detail of these synthesized materials. And there you can see the formation of the architecture, the HOMO energy calculated experimentally as well as theoretically indicates these molecules nature ambipolar in nature, and theoretically calculated data at VDFT also supports the experimental results, and thermal properties of these molecules are also very good and having the high melting point and good thermal stabilities. So getting the AI active property within these molecules. So this is the first time we have reported such kind of molecules. So having a particular acceptor core central moiety and adding these diarylamines and the cyclic heterocyclic there is amines and getting the AI property within that. So this is the first reports, our first report, and getting against the ambipolar charge transfer property in these molecules. So these can be utilized as a solid state emissive bipolar organic materials in optoelectronic devices. So these are research group, and first of all I thank the organizers, that is the UGC HRDC Center, Gujarat University, for giving me this opportunity to share my lecture or this talk and my research work in front of you participants. And also I thank these participants who have listened me patiently. So thank you.
Thank you very much, sir. The session has been quite an informative and encouraging one. Thank you for your valuable contribution.